So everyone, let's thank Ben. Ben is going to tell us about some cool stuff, very cool stuff in my opinion, about what's going on in the typed Racket world. Yeah.
Cool. All right. I'm delighted to announce that typed Racket, starting in the next release, 8.7, is going to have these two new things called shallow and optional types.
All right.
Can you explain what they are first? Okay, so what is typed Racket? It's a type system. It's also got some runtime components, but above all, it's a language. And typed Racket really is a family of languages. So there's at least three. There's two on the slide. There's normal typed Racket, there's typed Racket base, and there's the third hash lang that we don't normally talk about called typed Racket no check. So does anybody know what no check does?
I guess.
So no check lets you have typed Racket syntax and nothing else. It totally throws away the types. There's no type checking, and you just run the Racket program at the end of the day. Exactly like Python. So no check is the quick and dirty option if you want your code to run faster. So shallow and optional are two new languages in the family. So now under this umbrella we've got two additional options. You can switch your hash lang to typed Racket shallow, typed Racket optional, and now you're in this new world. So this is takeaway number one from the talk. We have two languages. It's not different types, it's not different parts of the type system, but two top-level things.
Wait, weren't optional already a thing?
No, optional was not a thing. No check was a thing. But no check doesn't run the type check.
There was like already an optional types library.
Thinking of optional contracts.
Oh, shit, you're right.
Yeah, the question is, wasn't optional already a thing? And the answer is no. Optional is new.
Optional contracts. Here I was thinking you meant an option type.
Yeah, option types were already a thing. Okay, but we're getting to optional. I haven't told you what it is yet. It's exciting. Getting the takeaway too. If you've got code that you've written in typed Racket, and the code type checks and runs, it's going to still type check in these new hash langs. So if you just switch the language at the top to shallow or optional, your code will still compile like before. So takeaway two, we've got exactly the same static types that we've already had. The language of those didn't change. And the way the type checker works doesn't change. So this begs the question, what is different? And that's performance. They have different runtime behavior for these types. The quick three-line explanation of this is that when you're running in the normal typed Racket, you're going to check everything when things cross between the typed world and the untyped world. In shallow typed Racket, we'll check just top-level properties of values that go across. And in optional typed Racket, there's no runtime checks at all. It's static only. So that's the top level of what the differences are. So yeah, the focus of this is really on runtime performance. And that's why I'm graying out no check, because no check was compile time only. So the focus is on these three. And to make it easier to talk about the three involved, I'll call normal typed Racket deep typed Racket, because it's doing these deep checks. We'll get to an example in a minute, but when a value comes across, it gets fully checked. When you're in shallow and optional, there's fewer checks. Cool. So it's all about performance. All right, and these are really the takeaways, right? We're 2 minutes into the talk, and here's what you need to know. Additional languages, same type checker as before, and now your performance changes. And so these languages lie on this continuum. We've got 3 points on this space now, and it goes from types that give you strong guarantees but have a high performance overhead on the left, down to the right, where you have very weak guarantees with the code runs, but they're faster. As Leaf put it very nicely, we have slow types on the left, and we have wrong types. Yeah, question?
And they're only slow if some code is untyped, right? If everything's typed, it's all fast.
Yeah, that's right. If your program is totally in typed Racket, then actually, well, there's more of it. If you're in deep typed Racket, yeah, everything will run fast. Deep pays a cost when there's boundaries to untype. So if there were none of those, then you were fast before. It was only at the boundaries that you'd pay. Yep.
So you have a cost at the boundary between these languages.
Yeah, that's right. We also have that.
Say that again, please.
There's also some cost at the boundary between these languages. Yeah, because these deep types have stronger guarantees than everybody else. So if deep talks to optional, deep doesn't trust the optional type. Because optional could, in some other communication, be talking with untyped. So there could be things all mixed up in the optional world at runtime. So when it goes back to deep, there's got to be another check.
Does it trust it at all?
It doesn't trust optional at all.
So does it know the things that optional checks and not check those? It checks everything.
It checks everything. It comes from optional. Maybe we can change that in the future. But really, the issue is optional can get very mixed up with the untyped world. So if we had some way of tagging this thing was statically checked, and I could take this function to the bank, then maybe we could skip the checks. But right now, we don't have that.
Does it trust shallow at all?
It trusts shallow just a tiny bit, not much. So we'll get to that too, yeah.
We don't even know what they are. We know all these things about them. Who they
Well,
trust.
this is what you need to know. If your code is running slow with deep, switch it over to shallow or optional.
Then it can be wrong.
Okay, let's find that we have an example. So here's a simple function, okay? The name is saysMove. Function saysMove takes in a list of symbols and returns a boolean. So we're going to search this list of symbols for the symbol moo. First, we'll check if the list is empty. If it is, that means we didn't find moo. We'll return false. If moo is the first element, we'll return true, and otherwise we'll recur and look in the rest of the list. So we're interested in boundaries. So let's have an untyped context call this typed function. And right now we've got it with blue, so that's for deep types. So this is the normal typed racket that we've had since Sancho Panachta came to the world. Okay, so there's a boundary here, and what is the cost that deep pays for running this program? What happens right here at this input type, list of symbol. So deep says, all right, I've got a value coming in from the untyped world. I need to check this entire value to make sure that it matches the static type that I've got up top. So that list of string has a guarantee in the deep world. The guarantee is that we really have a list, and it really contains only symbols inside. And so the cost is now this linear time traversal. This is one example of a deep check that needs to happen. And so, right, there's a cost to that. And this is implemented with using contracts, runtime boundaries with deep. So that's what deep does. Now for shallow. Same program as before, same untyped caller. There's 2 points to focus on here for shallow. First is the top domain type list of symbol as before, and we also need to look further down. And we'll get to that in a second. But first, shallow is weaker than deep, so the guarantee we have at the top is not the same guarantee that we had before. Instead of saying this is a list of symbols, shallow says, I'm going to make sure that this is a list, and I'm not going to check the contents. So this is a quicker check to run at the boundaries. But this isn't sound. I said list of symbol, so when I read elements out of the list in typed code here, there should be a symbol coming out, but that's not guaranteed. This could be a bad list. So that's why this car is another focal point. When we're in shallow type code and you read something out of a data structure, there'll be another one of these, what we call shape checks. So when we're pulling this element out of a list, there'll be a check right there to say, do we have a symbol? So the shallow type soundness guarantee says, I've got something that matches the top level shape of my type. In this case, the type is symbol, so symbol is just the same shape as symbol. We'll do a quick check for that. So this also means that whereas before in deep, all of our costs were at boundaries, when we're in the shallow world, our costs are spread out throughout the program. They're lower costs, but they do add up. Question? Yeah.
So if you gave it A, B, moo, 2, that would be acceptable because we coordinate before we check that card.
That would be acceptable, absolutely. So AB move 2, we would run down the list, and it's only when we pull something out of that that we find out what whether the element was good or bad. So if moo appears before the bad things, we'll never blow up on the bad things, and the program will just run. Yeah, but that also means that shallow, if it finds moo early, is going to pay a lower cost overall than deep, right? Because deep is going to eagerly walk through the thing, and shallow is just going to go lazily where I need to. Next question.
And is this, you say this runs on every time, does this mean it only runs on values that come from outside, or even if you call a function from within shallow racket, it will check in and come?
Yes, shallow within shallow does pay a cost.
Okay.
And so reducing that is a big problem. Actually, that might be a higher priority than reducing the shallow deep boundaries. Because what can we do within shallow to get rid of redundancies?
Right.
Yeah. But in general, the cost profile has been a lot better.
Is the cost really just list, or are you actually installing some sort of guard on the elements? Just list?
No guard whatsoever. Shallow is just
So
checking list.
the elements are guarded in some other way later.
Well, they're not guarded. The way that we get these element checks is by defending our typed code.
So you're gonna, but the defense is purely at the car call, and it's not sort of set up ahead of time.
Yeah, not set up ahead of time. So the values that you average is the values from before. There's no kind of chaperone on top of this.
How does typed Racket know what functions like take something out of the list? For car encoder, that's pretty easy, but what about more complex cases?
No, it all comes out of the base environment. Yes. And so this, I'll come to this later.
But you use the primitives that you use to create structs, right? All your complex data structures are made out of a common language of structure builders.
Yeah, well, okay. To a first approximation, everything needs a check. Every time I call a function, I've got to defensively make sure that it returns the right thing. To a first approximation. We do much better than that, but we'll come to that. Okay, was there another question?
A quick question. So it means that if you're looking through the list and you have some sort of mutating from like print or something, you will go through some sub-list before you get to the invalid value, right? So if you had an example where you have a list of symbols, the first three are symbols, and then you have a non-symbol, you will print the first three symbols because you're performing that check at the moment where you do,
all those side effects would happen. Yes.
They will happen. Okay. Thank you.
That makes me curious. So I put a printf on that first line, and we have the AD2. Yeah.
Actually, wait, what's the highlight? I should do the sure thing. Do you remove the key for slideshow to turn on the spotlight?
MRS, maybe with an alt.
I'm not risk it. I'll just use the
Control-C.
Okay. So we're right here on the first line. We have a print.
Yeah, if you do printf tilde s list.
Yeah.
And the list is got the 2 after the move. I'll see the 2 print out.
Yeah, you'll see the 2 print out. Okay. So to make sure this question is clear for everybody, what if at the very top of the function, we're inside this typed code, we have something that says the list of symbols, but we've only checked that it's a list so far. What if we say print the whole list? Since print is in untyped code, we cross a boundary. Untyped has no checks in it, so it'll print the entire list for us. Okay? So shallow checks are just local checks. That's the takeaway.
What if you implemented your own print in shallow type Racket that just used the untyped print for atoms, but you declared it as taking any?
If you declared it as taking any, okay, yeah. Where does the shallow check come from? We're saying.
Sorry.
No, this is an important point. Yeah, no, it's important because the runtime checks that you get in deep come from the boundaries that you have. Okay, so it's like I have a type annotation and then things get carried over. And this is nice because I can write the type in one place and then rely on it throughout the program. And in shallow, the checks are coming just from the local context that we have. So we know to check that there's a symbol coming out of here because this term that we're looking at that's highlighted has a static type symbol. So it just comes from the local static type. So if we've got our own print function implemented in shallow, the runtime check we get in there is going to depend on what's the local type for that expression inside print. So if it's any, and we pass the list of symbols into this print, which is looking at any elements, there won't be a runtime check to catch it in there, even though we're in shallow types. Yeah, so these checks are keeping you safe locally, just where you are, but they don't go throughout the program. And that's a tough point I was going to make later, but we make it now too.
It's too cool, man. We've got too many questions.
This is great. Okay, yeah. Well, that's how shallow works. We're experts at this point. Okay, and now for optional. If you switch to #line type Racket optional, there's no checks whatsoever. So this code runs basically as if it was Racket, even though we've got a boundary untyped code here. It's statically checked, and then it runs dynamically, just like TypeScript or other things that we love. Yeah. There's no guarantee, but there's no cost. No runtime checks. Okay, yeah, so we've seen this. To hammer it home, deep with these contracts at the boundary can get very expensive. So we saw a quick example using an immutable data structure list, and we said deep is going to eagerly traverse this thing. Things get even more expensive when we have mutable data structures or functions. They need to get wrapped when they cross a boundary. And there's a cost to allocating this wrapper, and there's going to be a layer of indirection later on, we call it. So all that cost is totally gone in the shallow world. We just have assertions, and we don't even have the assertions over in the optional land. Okay, Jay?
I don't like the name optional, and I want to workshop it here together.
Okay, let's save that one to the end. We're going to go to lunch after this. We'll have an optional table, and
Optional makes it sound like there's some, or like there might be some later sometimes.
The answer is no, Jay.
Am I missing that?
optional was not my favorite either, but it's really caught on.
Okay. I just want to see none. Like,
Maybe we can be the change.
Jay,
Also, we're in Racket. It's no problem to spin up another hash that we've got. Okay, yeah, we touched on this a bit before. So, remember, we started this off with that spectrum, right, between strong guarantees and high overhead, and weak guarantees and fast performance. So we just talked about the performance angle. Here's the guarantees angle, or another perspective on it. If you're coming to typed Racket and you've got a big untyped code base, and you start sprinkling types through it to help you understand what's going on and to debug, it's important to know that these types mean different things if they're in a different language. So we've got 3 types here that are all the same. Arrow string, which means I've got this thunk, and when I call it, it should give me a string back. I can only count on that in the deep world. Deep gives me the guarantee that this is really a function that's going to return a string every time I call it, and it'll halt the program if anything non-string comes out of the function. In shallow, we just know that there's a function. So if we set up a shallow type as an interface, and then some untyped value goes through the interface and goes back out to the untyped world, the only thing we know about it is the top level shape. So we know it's a function in this case, but then when we call it from untyped land, anything can happen. And this goes back to our print discussion from before. If we passed in our list to untyped print can just handle it. And there's no checks. And then, yeah, of course, an optional, it doesn't work as an interface. You get static checking and that's it. Only deep is reliable everywhere? Yeah, the second point is only deep will give you blame. So deep and shallow can both find mismatches that happen between a static type and a value. When deep finds one of these, it will trace it backwards. So it's got these chaperones on top of the value. It can say, okay, here's a trail. I called a function and I got a bad value. This function came from another boundary, and I'll point you back to that. This is the wrong type annotation that you need to debug. It's not necessarily the result that the function computed, but the place where the function went over, or where it was defined. Shallow does not do that at all. If it finds a mismatch between a string and a not string, it blows up right there. You have the line number, and it's up to you to work back. But you can always switch from shallow to deep and rerun the program and use the blame for that. Okay, so deep is the only one that has blame. We actually spent a lot of time looking at blame for shallow, and there's a strategy that can get us a set of locations to look at, but it was very, very expensive. It was more expensive than deep types. So that's the one that's written down. Things are a lot simpler too. I'm not having it there. Jack?
Can you get it to do something where, like, in tests, if it finds a type error in shallow or untyped, it just automatically reruns them with deep?
That would be a cool thing to implement. Yeah, we don't have that now. Okay. The question was, wouldn't it be great to have a testing framework that it runs your code, it sees if there's a mix-up in the shallow world, automatically reruns it deep? And I think that would be an awesome tool to have. Right.
Is there an operation in shallow to deepen the checks around a value?
Is there an operation in shallow to deepen the checks that it does? Maybe we have a couple of pairs and we want to look more than one level deep. No, we don't have that yet. Okay, so now we understand this continuum a little bit better. Okay, Jack, one more.
So it has to be on a whole file basis, like deep versus shallow checks.
Yeah, deep versus shallow is a whole file basis.
Whole file or whole module?
Whole module.
Okay.
Okay, again, these things are out. They're released in Racket 8.7. You can try them out now and nightly. If you were here 2 years ago, though, you might be wondering, wait, weren't these announced back in 2020? Did we get lost? I've got 3 reasons, and 2 of them are pretty good. What's it so? Okay. Number 1 was life stuff. Most of it was good. Graduating, we have a new member of the family. These things all kept me away from typewriting. So that's the bad reason. Good reason number one is now that we have these 2 additional languages, there's 4 that potentially want to communicate with one another. So wiring these up so that they can each safely talk took some time. So you can read about the details in a paper. Read about the details in PLDI. The takeaway is if you're moving between these typed languages, if you want to move from deep to shallow, shallow optional, they just need to require one another. Okay, so there's no extra syntax for this boundary versus this boundary. It's all typed land in terms of what you have to write down. Just require works. And then if you're in the untyped side, if a value comes from untyped to typed, you need to write require typed, just like before. Okay. But yeah, the real trick with this was getting a 1-line change if I go from normal typed racket to shallow typed racket. I just change the hash line and nothing else. And that's basically true. There's a few corner cases, and there's 2 of them down at the bottom. Really, it's if you're working with an API that lets you manipulate what happens at a boundary, then you knew you were in trouble. Okay. These need some work with shallow. So define typed untyped ID, for example, now takes 2 additional arguments to say, what do I do in a shallow context and what do I do in an optional context? Okay. Also, macros across a boundary is tough. So this is an excellent thing to work on, is can we see whether a macro is safe to export from a shallow context into a deep form? Right now, you have to analyze the macro yourself, and you can say, I'll unsafely provide it. Jay?
For both of those, and in particular the defined typed untyped, going from requiring 2 names to requiring 4, is this an egregious violation of Racket's promise of backwards compatibility?
I'm very glad you asked.
Or does it like default to something that is like safe but slow?
Well, it's not safe. It does have a default. The default is 2 arguments. So if you had code that ran with 2 arguments before, you still have that with defined typed untyped. The extra 2 arguments are optional. And yeah, the safe but slow, really, the problem is this guy, define typed untyped. This is a wild form. I get 1 name, and I can have up to 4 different meanings for it. So back in the past when I had the 2 meanings, they don't need to be related at all. Okay? The idea was one is going to have boundary checks and the other one is not, but that didn't need to be the case. So we have a reasonable default, but it might not be a safe default if you had 2 crazy things stitched together.
And the new default is presumably the typed one?
You get the protected one, usually. Yeah. Or what should be the protected one, nominally. Okay, that's reason 1. Reason 2 is we spend a lot of time making shallow faster. Okay, and the one thing that I'm really proud of is what we had the question back here before to relate to base types, base environment. Okay, so really quickly, let's go into the context for this change. I mean, the takeaway is things run faster. The context is, in the naive implementation of shallow, technically every function call sitting on our program is going to need some kind of a check. So we have car here, yes, we need a check, but there's a few others like null and cutter. And just looking at this, we can say we don't have to check those. We know that they're going to return values that match the shape that we're expecting. But shallow doesn't know that unless we somehow tell it to. So what we had originally was this first order solution where there's a list of identifiers that you can trust. The result that comes out of cutter, the result that comes out of map is shaped for shapes. Safe for shapes. This doesn't work for higher order based types. So I was really glad that with Sam's help, we were able to fix it. So now we have internally in typed racket a notion of whether this function returns something that I can trust. And now, since it's part of the type, it's compositional. So we have a much better base environment. There's still a lot of hand annotation that went on in this base environment. And we think that we can get rid of that with a simple rule, which is if the type of my function here is polymorphic and it's returning something that's an alpha, that's when I need to check. And if it's not an alpha in the base environment, I don't need to check that. So that's something to look at and hopefully implement in the future. Okay, so this was a big change and that wasn't there in 2020. And yes, hopefully there's much more to come. Better cooperation between deep and shallow. We touched on a lot of this before. Can we make shallow faster and less redundant? And can we get macros and occurrence types to go across shallow boundaries? Oh, right. And everybody wants to know about the math library. For years, we've got this warning on top of some of the files. Like, for example, here's math arrays. And it says, don't use this if you're an untyped client. You could be 25 to 50 times slower. So hopefully now that we have these languages with low overhead, we can we can get rid of this warning. It's not totally straightforward, but you can follow along with the issue there. And maybe at next RacketCon we'll have a happy answer. Okay, that's the end. Those are the 3 takeaways, and there's time for a few more questions.
So the issue with the math library, right, is that it's hard coded in the repo. That's like #type bracket and not type bracket, shallow or optional, right? So do you think that there should be a way for client to modify this language just for the coded interaction?
Yeah, okay, so math library is slow for untyped guys because it's all written using this type bracket deep, the normal type bracket. So should we change the whole library to be using shallow types? Well, we don't just want to do that because it's going to slow down our deep clients. So the untyped guys will get a lot faster, but the typed guys will get a bit slower. So I think we want something where there's 2 options for the math library. So there's math typed and math untyped. And hopefully by having these languages with the same syntax, it's easy to implement this sort of thing.
Submodules.
Some modules.
Automatic
We
submodules.
really want one source code, yeah, and then different.
Hash include.
Hash include.
That's the way we did things in my day.
Milo?
This had come up before during some of the retro typing stuff, but we know that if you switch from deep to shallow, clearly there's some cases where it might not error as much. Like we had the example where the number comes after the end and it doesn't error, or like it does error. Are there situations where shallow produces like a different result than deep, but doesn't error? Like the behavior of erroring?
Well, it definitely, can shallow ever produce a different result than deep? We know that sometimes it can not error when deep error. And it can definitely produce different results up to shallow, because these wrappers are no longer there, and that's something that we can observe. I don't think so, though. I think the base level values are the same. I mean, that's certainly what the theory says.
You can catch the exception and then return 42.
Yes.
Good EQ. Good EQ.
Oh, EQ will, yeah, that'll look based on the shaft rows, right? Question here?
What does make predicate or cast look like in shallow?
Yeah. Cast, what does cast do in deep versus shallow? Cast is weaker in shallow. Okay, so you can think of cast just like our boundary checks. It's not checking just the top level tag. Make predicate. Make predicate was a tough question, and we went back and forth. So right now, make predicate is the same, I think, in all of these languages. You get the same eager predicate from make predicate. Ben.
So for the deep type checks, if you have like a large data structure that crosses back and forth a lot, probably doesn't change a whole lot between those. Is there any caching for some substructures that haven't changed at all?
No, and this is another great research question. How can we speed up deep for things that don't have a wrapper on top?
If there's more subtypes of the type bracket being planned, then it looks like there's like a quadratic overhead of the number of interactions you'll have to make. Is that sustainable? Or is there anything like that planned?
Yeah, right. So we have all these different languages. They all need to know about one another. What are we going to do about this communication flaw? And that's an open question. It's still an n-squared problem.
It's called being an assistant professor.
He was on first.
Okay.
Or maybe,
Go ahead. Jay, please.
The thing where you said you have an annotation in the type system for knowing how much you can trust the result of a call.
Yep.
This feels kind of like the whole thing that occurrence types already do with the guards, where this check I now know that I've learned some true thing about the values. Isn't it an extension of that? Is it different? Can it be used inside of deep programs too to learn something more? Or am I misunderstanding?
Yeah, it's different. It's just right now for letting shallow know I don't need to look at this. And that's a good question if we can integrate it somehow with occurrence typing. The big question on my mind with occurrence typing is, can we use these rich occurrence types that we have to make some shallow checks go away? Because right now, if you access the first element of a list twice in shallow, you're going to pay for it. And I feel like with occurrence types, we can get rid of that.